Step A is to get eigenvalues. At this point, you do not have to recall the geometric meaning. You just remember a eigenvalue of a matrix or a linear transformation is a number. Okay. Now, how can we get this number? To get this number, you compute ti minus a first. Ti, you remember the meaning? You treat t as a unknown. Okay. And the t is a eigenvalue. But we're trying to solve an equation for eigenvalue, right? You compute ti minus a first, okay, and then you compute the determinant of ti minus a. As long as you know what's going on, you can start with the determinant. Again, if A is a 3x3 matrix, I is also a 3x3 matrix, right? I mean 3x3 identity matrix. Okay. Compute ti minus a, and then you can get the determinant. I told you the trick before. Ti minus a is always in the following form, and you get the negations. You know what I mean by negations, right? The negatives of all the numbers in A. So do you see -1, -1, so -1, so -2, and so on, right? You get the negations of all the entries in matrix A, and then you just add t to the numbers on the main diagonal. Okay. This diagonal is called the main diagonal. Okay. The answer to the determinant is always a polynomial of degree. If A is a 3x3 matrix, it's a polynomial of t. The degree of the polynomial is in general 3. Okay. Your target is to compute the determinant. For the purpose of doing the exams or test, finance coming soon, you are going to see a row or column consisting of all zeros. Okay. I'm also testing how to compute the determinant using eigenvalues stuff. Okay. Compute the determinant using the last row. So because the last row has 2 columns. Okay. And then you need to recall how to compute the determinant, the number at the 3, 3 location. In here you have a cofactor. In a cofactor, so there's a sign involved, right? So this sign is it's because this entry is at the 3, 3 location. So this one, the cofactor, okay. I mean the sign for the cofactor is determined by -1 to the power of 3 plus 3, so it is 6. I believe you can remember this. All of you guys have no problems to evaluate the determinants. Okay. After that, you compute the determinant. Eventually, to solve the equation for eigenvalues, you need to factor the polynomial. Okay. I'm trying to say if you have a factor of t minus 1 in here, so do not multiply them out. Okay. So keep the factored form. And then for the determinant of the 2x2 matrix, you have that. For this one, you have to break down and factor. By break down, I mean you multiply them out, okay, and then you factor the solution to the and then you set the determinant. I told you the determinant is in general a polynomial of degree 3 if A is a 3x3 matrix. Okay, and then you set the determinant to be 0. You have an equation. This equation has a name, characteristic equation, right, of the matrix. Solve the equation, you have eigenvalues. Okay. In this particular case, you have 2 eigenvalues. You have 2 eigenvalues. It's because you have t minus 1, the whole thing squared in here. And then for each eigenvalue, for each of the 2 eigenvalues, you find the corresponding eigenvectors. In order to get all the eigenvectors, we need eigenspace, right? Eigenspace is the set consisting of all the eigenvectors, so together with the 0 vector. Okay. You need to repeat for however many of eigenvalues. in this particular case, you need to repeat twice for each of the two eigenvalues. For each of the two eigenvalues, you need to repeat the thing once. Okay. To get the eigenspace, now let's recall some details. In item number B, we find the eigenspaces. Repeat twice. Okay. For eigenvalue of 1, I told you why last time, but the bottom line is try to memorize the form of the equation. And by the way, you do not have to memorize. I have decided the final exam is going to be open book, so but no internet, no browsing. You have to use internet, of course. No web browsing, no web surfing. I mean, okay. Nowadays the internet can do too many things. You can get the inverse, I know. Okay, you can get REF. You can do everything. You can get everything with many steps. Okay, it's kind of weird. No web surfing. Okay, as long as you show your face, I believe I can tell if you are surfing the internet or not. Okay. There will be an email with more details. Okay. Anything on not the bottom line. Okay. Anything on paper is okay. Anything on paper is okay. If you could print many things, everything on paper is okay. If you want to write notes, okay. Textbooks, okay. So what everything on paper is okay, but no surfing. Actually, it's because you guys asked about the final, I was thinking about that. So that's kind of my decision. Okay. I'm saying that to the class. I'm not going to change my mind. Okay. Simple. So, still, you need to know where the equation is coming from. Okay, I told you why last time. So the form of the equation is here, and then you just have to know the meaning of everything in the equation. This vector equation corresponds to a system of 3 equations with 3 unknowns, actually a homogeneous one. I said homogeneous because all the constants are zeros. Okay. Using a particular value of t, using a particular eigenvalue. Okay. And of course, for the exam, no discussions. You have to do everything independently. Okay. I know some of you guys might want to write the exam at the same place. It doesn't matter, but do not show your work to other people. So do not let the third person transfer the paper to another person. Trust me, I can tell. I have seen the problems last year. I have seen all kinds of problems. You know, identical wrong answers is cheating in math. It's almost always the case. Okay. This time I have decided I'm going to report if I see cheating. It's the final exam. For quizzes, I don't care that much. Where am I? Okay. Equation. Okay. For the particular eigenvalue, now let's say t1, t sub 1, you solve the equation in here. Okay. If t1 value is 1, the system becomes that. V is the vector consisting of all the unknowns. I think on the course manual I was trying to use x, y, x2, x3, but it's also okay to use x, y, z, the same thing, right? You have seen the same thing. And then I minus a is the matrix of coefficients. You compute I minus a, right? And then to solve the system, or to solve the vector equation, ABC thing I haven't decided yet. Yeah. I want you to show your face on web camera anyway. I haven't decided. So I have been using too many versions of the exams, and it's hard for me to make up questions. And when it comes to marking, it's hard for me too. Okay. I haven't decided using ABC thing or not. Okay. So probably not. I haven't decided. Anyway, for each value of t, you get a system, okay, and then you compute I minus a in this particular case. So you have the matrix of coefficients. Okay. To solve the system, to solve the system determined by the matrix equation, you use the augmented matrix. You do not have to recover the system. I believe you have seen that many times. You just get the system and then REF, right? Perform row reductions, make the matrix into REF. I want to remind you, so do make sure the final form is in REF before getting the general solution. Okay. I know some people could be more confused for simpler questions. I'm trying to say the last matrix is indeed in REF, row reduced echelon form. After getting this, so don't be scared. You just follow the routine. The same thing. The circled one is the leading one of row 1. Two others are not leading ones, right? So you just have one row consisting of non-zero numbers. But so you have two columns without leading ones. So the same thing. You set y and z corresponding to column 2 and column 3, right? To be the parameters, right? And then you solve the first equation. The equation determined by the first row for x. Write x in terms of r and s. Okay. That's how you get E1. E sub 1 is actually, we call that the solution set to the system. The system is homogeneous. Okay. For a homogeneous system, the solution set is automatically a subspace. Probably I mentioned that before. Okay. So you have the subspace E1. If I do not ask you to verify, you do not have to verify. I'm trying to say you do not have to show E1 is a subspace by verifying the three conditions. Close under vector addition. I'm trying to say you do not need to. Okay. In question B, I'm just asking you to find eigenspaces. So the name for that, the name for E sub 1 is the eigenspace for the eigenvalue of 1. Okay. The standard notation. And then you repeat the whole thing for the other eigenvalue. We have two eigenvalues, right? The other one is 3, the eigenvalue of 3. You repeat the same thing. You plug 3 into that equation. You see the equations here. Okay. The equation is t2i minus a. I did not write that in here. Okay. In any case, you replace t value with 3, and then you have a system. Now the same thing. Solve the system. Okay. The augmented matrix for the system of linear equations determined by the matrix equation is that. Okay. Put it into REF. You see there are too many ones, many zeros already. It's simple, right? Show your work. You have to show your work in here. And then this is the final form. That's a matrix in REF. Okay. Column 2 is a column without leading 1. Set x2, set y to be a parameter. Okay, you could use r, it doesn't matter. Okay. And then solve the first equation for x1. So x1, for x is r, right? I'm trying to use x, y, z. So in this case, right? And then the third component, you have no other choices. You look at the second line. The equation determined by the second line tells you z value is equal to 0. So that's how you get the general solution. In the general solution, R is a parameter, meaning R can take any number, right? R can take any real number. So you have the eigenspace for the eigenvalue of 3. Okay, now we move on to the new questions. I will show you something cool. At least I can see. I told you eigenvalues and eigenvectors, so this thing has too many applications. We do not have time to talk too much about that, but I want to show you something cool. Okay, very shortly we can compute the high power of a matrix. So by that I mean if you want to multiply A 10 times without eigenvector stuff, you would have to multiply the thing 10 times. So how about we do it 100 times? Okay, so later on we could try 100 times. If you compute by hand, it's kind of so not possible, right? But with diagonalization, we have a way to compute high powers of a square matrix, as long as it's diagonalizable. You are going to see the terms very soon. Okay, we'll move on to do more questions. But now let's concentrate on question. Okay, I do want to make sure. The non-zero vectors in E1 are indeed vectors. Are indeed eigenvectors. So how about we choose one particular eigenvector? Okay. So now let's say we choose a vector. The following is designed to convince you E1, E sub 1 eigenspace is indeed consisting of all the eigenvectors for the eigenvalue of 1. Okay. Now let's choose one particular vector. So how about we use R value of 1 and S value of 1. I was trying to write 0. So how about we just use 1? And then the first component is determined by R and S. You have no other choices for the first component, which is -2, right? Now I want to convince you that that particular vector is indeed an eigenvector. To show its eigenvector, I forgot A. So how about I was trying to use A to denote the matrix. Okay. For some reason it's gone. Now I'm trying to compute the output for the input of -2, 1, 1. Okay. We want to show it's indeed in the same or in the reverse direction as the vector. Okay. The given matrix A. I think I can copy this matrix into here. That's the matrix A, right? If you want to compute the matrix A, so times -2, 1, 1, the answer is going to be a column matrix. So by that we mean the output is going to be a vector. Okay. And so anybody want to tell me very quickly how to solve this one? Okay. First row, that column. If you actually compute, I want you to actually compute. I hope you are going to get -2, 1, 1. Now let's just check one number. Okay, the first row times the column, -4 plus 1, and then plus 1. You have -2, right? Now let's check all the columns. Okay, 1 times -2, and then plus 2 times 1, and then plus 1 times 1. I believe you have 1. Okay, what I'm trying to say. For this particular value v, so you have the property that a times v. Thus the output for the input of v is equal to v, right? Or you can write that as 1 times v. Okay. So do you see the output of v is the same as v? It means v is a eigenvector. You remember the definition we mentioned last time, and the corresponding eigenvalue is 1. Okay. So by that I mean I did that, so just wanted to convince you v is indeed a eigenvector for the eigenvalue of 1. Okay. And likewise, you can choose any vector from E sub 3 as long as the vector is non-zero vector. Then you can see you could check. So a times any vector, so now let's say in the form of RR0, I'm pretty sure if you actually calculate, it's going to be 3 times RR0. So which means RR0 as long as R value is a non-zero number, and then that's a eigenvector for the eigenvalue of 3. Okay. You're going to see at least one application, one cool thing about eigenvectors very shortly. Okay. But now let's move on to question C. Okay. You look at C. In C, I'm trying to get a basis for each of the 2 subspaces. E sub 1 first. Okay. I'm not asking you to justify. You just tell me a basis. Okay. So now let's say a basis. I'm doing question C now. Okay. A basis. A basis of E sub 1 is, you see you have two parameters. By that I mean the second column and the third column can be any number. I think we have seen this many times, right? You use R value of 1 and S value of 0. You can have one of the 2 basis vectors. Okay, and then you use R value of 0, S value of 1. You can get another one. Okay. So a basis of E1 is one vector is determined by R value of 1 and S value of 0. If R value is 1, S value is 0, then you have no other choices for the first component, so which is -1, right? And then the second basis vector is also -1, 1, 0. I believe you see what's going on here. Okay. We have seen this many times. R value of 1, S value of 0, so determines that vector. R value of 0, S value of 1. Why do I write the same thing twice? R value of 0, S value of 1 gives you that, right? Okay. Sure, thank you. Heard it. I spotted that. And then you're done question C. Again, if I'm not asking you to justify, you just get a basis. And by the way, the dimension of E sub 1 is equal to 2. It's because you have two basis vectors in that basis, right? Okay, now let's get a basis of E sub 3. R is a parameter, right? R can be any number. So a basis of E sub 3. You can see the dimension is 1. So basically R value of 1 will determine a basis vector 1, 1, 1, 1, 0. actually the same trick. If you want to verify, you could verify, but I'm not asking you. Okay. Each vector in the form of RR0 can be represented as a linear combination of that vector. The coefficient is just R, right? I'm trying to say the scalar is just R. And the one non-zero vector is automatically linearly independent, right? Okay, so we're done. We're done question. So that's question C. So we're done C, right? So that's part of C. We move on. We move on to D. Okay. So temporarily, you do not have to care too much about the meaning. So how about I will tell you the meaning very shortly, but I will tell you the condition if a matrix is diagonalizable or not. Okay. I know it doesn't make too much sense without knowing the meaning. I tell you the condition, but it's going to be clear soon. Okay. For question number D, I want you to determine if the matrix is diagonalizable or not. Okay, I will tell you the meaning very shortly. Okay, but I want to tell you the condition first. Okay, you listen to me carefully. If I'm asking why, I'm going to write down why. Okay. For question number D, I'm going to write the wording. But to answer why, you count how many basis vectors altogether from all the eigenspaces. Again, I want to repeat. To answer question D, you count how many basis vectors altogether from all eigenspaces. In E sub 1, you have two basis vectors, right? In E sub 3, you have one basis vector. You put them together. Altogether, you have 1, 2, 3 basis vectors, right? Again, you count altogether how many basis vectors from all the eigenspaces. Okay. If the number is equal to the number of rows or the number of columns in matrix A, and then the answer is yes. In matrix A, you see we have a 3 by 3 matrix, right? The number of rows is equal to 3, the number of columns is equal to 3. And by the way, you can only talk about eigenvalues and eigenvectors for a square matrix. So by that we mean a 2 by 2 matrix, 3 by 3 matrix. In particular, the number of rows is the same as the number of columns, so which is 3. Okay, which is 3. You remember that 3. And then you count how many basis vectors altogether, right? Altogether, you have 3. So the answer is yes. Okay. So how about we just use answer the question in terms of the dimension. The dimension is clear. I know it's not a part of C, but in order to answer question D, I want to specify a condition. The condition under which the given matrix is diagonalizable. Okay. For E1, I'm going to write the dimension of E1 is equal to 2. I think you know what's going on, right? So it's because in a basis there are two basis vectors in the basis. Okay. And then the dimension of E sub 3 is equal to 1. Okay. Now I'm going to answer question D. Okay. Okay. The answer to D is yes. I will write the full sentence. The matrix A is diagonalizable. Because I will give you the condition. Okay, the condition, I'm going to state the condition in terms of the dimension. Okay, the dimension of E sub 1, so which is the same thing as the number of vectors in E1, right? E sub 1. Okay, and then plus the dimension of E sub 3 is equal to, you see it's 2 plus 1, right? So which is 3. So this 3 is the same as the number of rows or the number of columns in matrix A. Okay. That's why if the total of the dimensions, I'm going to rephrase the condition under which the given matrix is diagonalizable. In other words, if the sum of the dimensions of all the eigenspaces is equal to the number of rows or the number of columns in A, and then the answer is yes. Otherwise, it's no. Okay. So you see, that's yes. Okay. Again, I haven't told you the meaning of diagonalizable or not. Now we move on to question E. Okay. After E, so you are going to see the meaning. Actually, the definition is in the statement of question E. Probably I do not have too much space in here, but what do I do? Sorry, I was trying to duplicate that slide. Okay, now I'm going to move on to E. Okay. Actually, the definition of diagonalizable is here. Okay. So maybe I'm going to write down the definition. Okay. Now the definition. What we mean by a square matrix is diagonalizable. Okay. A is said to be diagonalizable if you can find a formal wording as there exists a invertible matrix matrix P such that to the left you multiply the inverse of P, and then you multiply A, and then you multiply P. So to the right is equal to D, where D is a diagonal matrix. By diagonal matrix, we mean all the numbers on the I'm trying to say the only numbers on the main diagonals. Now let me try again. The only non-zero numbers are the only possible non-zero numbers are the numbers on the main diagonal. I will show the meaning. Okay, I will show the meaning. Now, for instance, I'm going to remove this. Okay, so now let's say 1 1 1 1 2. All other numbers are zeros, and by the way, the main diagonal is the diagonal from the top left to bottom right. So that's the main diagonal. Okay, that's a diagonal matrix. So because all other entries are zeros. So do you know what I mean? It's also possible to have a number on the main diagonal, so to be 0. So that's also a diagonal matrix. Okay. The definition, I'm not going to write it down. I said the only possible numbers that are non-zero numbers are the numbers on the main diagonal. It's probably is a little wordy. Or you can say something like all the numbers not on the main diagonals are zeros. It's the same thing. So yeah, probably that's better. Okay. But I think you know the meaning of the diagonal matrix. Okay. It's kind of using an invertible matrix P. You can make A diagonal. So can I say that way? Using a invertible matrix P, you can make A diagonal. How to make it a diagonal? You multiply the inverse to the left of A. Okay, you multiply P to the right of A. Okay, so that's the definition. Now the amazing thing is after getting eigenvalues and eigenspaces, okay, after getting the basis, we can actually determine P. We can find the P. We can find the D. Okay, I will show the cool thing very shortly. Okay, okay, so duplicate the slide again. On the new slide, I'm going to remove the definition. Okay, now we're going to do question E now. Okay, we're ready to do E. Actually, to do question E, we need to find two things. We need to find the diagonal matrix, right? We need to find the P. Okay, I will show you how to form P and how to get D. Okay, now let's get D first. D is supposed to be a diagonal matrix, a 3 by 3, it's a diagonal matrix. Okay. Actually, to be diagonal, all other numbers are zeros. I'm just looking for 3 numbers. Okay. Anybody want to guess the 3 numbers? Or have you seen this before? The 3 numbers are on the main diagonal are eigenvalues. I want to repeat, the 3 numbers you are looking for are eigenvalues. Okay. It's corresponding to the dimension. You see E sub 1 has 2 eigenvectors. The dimension is equal to 2, right? So you need the 2 eigenvalues corresponding to E sub 1. I want to repeat, why do I have 2 ones? It's because the dimension of E sub 1 is equal to 2. The number of eigenvectors on the main diagonal is determined by the dimension of E sub 1. Okay. Okay. And then, likewise, anybody want to tell me the number at the 3, 3 location? It's 3. We have 2 eigenvalues. One eigenvalue is 1. The other eigenvalue is 3, right? So this number we need is 3. I missed a 0 in here. Again, we need 2 ones. So because the dimension of E sub 1 is 2, I need 1, 3. So because the dimension of E sub 3 is equal to 1. Okay. That's how you get D, the diagonal matrix. You are not done yet. The cool thing is you can also get P from eigenvalues and eigenvectors. Okay. Matrix P. Matrix P is formed by the basis of the eigenspaces. I want to repeat, P, I mean the columns of P are determined by the basis of eigenspaces. You look at the mouse cursor, okay? If you put 1 in here, the first column is, the first 2 columns you have two ones in here. The first two columns, they are coming from the basis vectors of E1. So you have -1, 0. So temporarily, you do not see y. You just remember. Very shortly, I will convince you it's indeed true. Okay. -1, 0, and then 91, 91, 1, 0. And then 91, 0, 1. I'm looking at here. Okay. You put the two basis vectors of E1 in columns to form the two columns of P. Okay. And likewise, you know what's going on with the other one. Okay, it's 1, 1, 0. That's how we get D, the diagonal matrix. That's how we get P, a invertible matrix. Okay. Okay. So any questions? You just remember that how to, after you know how to get the basis of E sub 1, E sub 3, and then all you need is to remember how to get the D and how to get the P. Very shortly, we're going to verify it's indeed true that P will make a diagonal matrix. Okay. Actually, that is the next question. I hope I have to copy everything in. Okay, so we're done question E. Okay. Now we'll do this. Two is to do the question on the screen. Two ways to verify that. Okay, one way is longer way. It's possible to find the inverse. You have a way to get the inverse, right? So very shortly, I'm going to recall that. But there's one other way. There's one other way. You look at what I read. Okay. This equation, the inverse of P and then times A and then times P is equal to D. So this equation is equivalent to if you multiply two sides of the equation by P. So now let's see what's going on. Okay. Starting from that, if I multiply two sides of the equation by P, you have P times P inverse and then times A and then times P. You know, matrix multiplication is associative. It doesn't matter how you group, okay, as long as the order is not changed. Is equal to PD, right? So do you see what's going on? That equation, I'm trying to say that equation is equivalent to that as long as P is invertible. Okay. You see how I got that? You multiply two sides of the equation by P. Sorry, I forgot something here. Okay. And then, what is that? The stuff in the brackets. It's identity, I, right? Yeah, it's I. It's identity, I. So thank you. Go. I'm trying to say the given identity is equivalent to AP and then times PD. Okay. If I want you to verify that, you could do it in two ways. One way is to actually compute the inverse. Very shortly, we'll see that. Okay. The other way is instead of computing the inverse, you can just verify that. Okay. as long as you know P is invertible. We'll do it the shorter way, okay? The shorter way. AP is equal to PD. You could just remember that, okay? Now for question F, I'm going to write it down, okay? We verify the inverse of P and then times A and then times P is equal to D by checking, by verifying, by checking AP is equal to PD, okay? Can I stop here? You know how to compute AP, you know how to compute PD. For the final exam, I actually want you to really compute AP and PD, okay? Multiplying two matrices. Okay. I'm trying to use a question like that to check matrix operations, in particular multiplication, okay? I'm looking for the answer of two sides. So maybe you can write something like, in fact, AP is equal to whatever 3 by 3 matrix. AP, I mean, okay. And PD is equal to whatever 3 by 3 matrix. And then you say, so it's indeed true that AP is equal to PD. Okay. Trust me, it's indeed true, okay? It's indeed true. I'm trying to say, if you just have question F, you can do it that way. But in order to do question G, we have to compute the inverse of A. I mean the inverse of P. Okay, it's I know it's long, but I got that ready before the class. Okay. You remember the details? You form a 3 by 6 matrix, right? To the left of the bar you have A, and then to the right of the bar you have I. You remember that? Now we are going to get the inverse of A. We call the algorithm. Okay. And then you perform row reductions to make the matrix into REF. Okay. Now it's indeed true. To the left of the bar, you are going to get identity matrix. You could check that. Okay, you could check that on the assignment. You are going to do the same thing for a different A, a different 3 by 3 matrix. Okay. After doing this, you can get the inverse of P. Sorry, I use a wrong notation here. It's supposed to be P. We're trying to get the inverse of P. So it's good enough. After you see in the final form, the matrix to the left is a identity matrix, and then you can conclude P is indeed invertible. We wanted P to be invertible, right? And then the inverse of P is coming from the matrix to the right of the bar. So which is, I'm going to copy it down. Okay, -1/2 and 1/2, and then -1/2, 0, 0, 1 in the second row. The last row are 1/2. If I did not copy any numbers wrong from the website, I told you it's possible to do anything from some website. That's the inverse of P. Okay. Now I'm going to show you the cool thing about the last question. Okay, did I copy it already? Okay. Now we're going to compute a to the power of 10, or you could compute a to the power of 100. Okay. Actually, the high powers of invertible, I mean the high powers of a matrix, a square matrix, is useful in other places. Okay, so you can treat that as one application of eigenvalues and eigenvectors. Okay, actually I told you earlier, eigenvalues and eigenvectors have too many applications in other places. So differential, so equations, and so on. So probably some of you guys are going to take that course, ODEs. Okay, anyway, we're going to get the a to the power of 10. A to the power of 10. Okay. I will show you some details. Now it's true that a times a is diagonalizable. We know p, right? We know the inverse of p. So a is equal to the inverse of p, and then let me try again. I think I wrote something wrong already. Okay. I'm trying to say a is diagonalizable. It means the inverse of p times a, and then times p is equal to the diagonal matrix D, right? I think you have seen P, you have seen D. D is here, 1, 1, 3 on the main diagonal, okay. And the P, you remember how we got P? Anyway, from that equation, we have a way to compute a to the power of 10, a to any power. Okay. From here, I'm going to multiply two sides of the equation by p on the left. Can I do that in 2 steps? By p on the left. Okay, I do not have to write a new line. By p on the left, and by the inverse of p on the right. And of course, you have to do the same thing to the right hand side. I'm trying to say you have p on the left, you have the inverse of p on the right. Okay. Again, matrix multiplication is associative. So by that we mean you can regroup them any way you want. So do you see the stuff inside the brackets are i's? It's because p inverse times p in whatever order is equal to I. Okay. So the left hand side is nothing but a. Okay, it's a, and then a is equal to p times d, and then times p inverse. Okay. After that, and then we're ready to compute the a to the power of 10. So how about we start from, okay, now let's just start from, so how about, okay, it doesn't matter. So we just go directly to 10th power of a, okay, 10th power of a. So by that I mean you replace a, it means a times a, then times a, right? And then you multiply a by itself 10 times. So you have 10 of these. I never know how to write that properly. Yay, I did that. So questions? Questions? So mute your microphone, please. I muted you. Okay, you multiply a by itself, so 10 times. Now you're going to see what's going on. Now for each a, you replace a with PD P inverse. PD P inverse. That's the first a, okay. And then PD P inverse. That's the second A. You keep on doing. You have 10 of these. PD, P inverse. For the people who are in calculus, it's kind of the series. I told you the telescope thing. I think you did a question, so something like this. It's comparable to this, so it's not the same thing, of course. Okay. Now something cool is coming. I told you matrix multiplication is invertible. Okay, you can regroup the factors in any way you want. So how about, so this time I regroup these two. You see that's I, right? That's I. And I times any matrix, you can remove I. I mean, I is comparable to 1, right? 1 times any number is equal to any number. I hope you can see what's going on. Eventually, there remains only a P on the left, and then you have D. You multiply that D, you look at the mouse cursor, okay? That D and that D, you have D squared, right? I'm trying to say you can cancel out all the P inverse and the P's, so in the middle, okay? There remains only 1P on the left, and then times D to the power of 10, and then on the right you have the inverse of P. Do you see that? It's cool, right? I'm trying to say for a diagonal matrix, it's super easy to compute high powers. I will give you a formula. You could verify later. Okay, you could verify later. But how about I just show you what's going on here. Okay, so now let's say for a 2 by 2 diagonal matrix. So now let's say 1 2. So how about we use 2 3? Okay, 0 0. If I call that matrix, so now let's say B. If I want you to compute the B squared, it's easy to verify. It's B times B. You could do it so very quickly. Okay. So do you see it's 4 9? It's actually 2 squared, 3 squared on the main diagonals. And likewise, B to the power of 10 or B to whatever power n. Can I use n for 10, for 100, for 10,000? So this thing is equal to 2 to the power of 10, and then this number on the main diagonal is going to be 3 to the power of 10, right? I'm trying to say for diagonal matrices, it's super easy to compute the high powers. You just take the powers of the numbers on the main diagonal. Okay. Now let's go back to this. Okay. Now let's go back to this. Now to compute a to the power of 10, all we need is to compute p times d to the power of 10 times the inverse of p. Okay.